All right. Good evening, everyone. Welcome to class. And this is not our normal class that we do have on weekends. It's a necessary class because we are kind of lagging behind. So it's necessary that we have this class. Right. So the stuff we do in our class, like signing attendance, won't apply to this class. So we're not going to be signing or marking any attendance for this particular class. It's not a compulsory class, but it's a necessary class because what we're going to be covering in this class is actually part of our curriculum, right? So I'm just bringing out time to ensure that we cover everything that we need to cover. So yeah, the recording will be made available as usual. So for those that are unable to meet up with class, it's fine. I understand that some of us might have schedule that would not be convenient. So you can always go back to the recording and all of that. And this class would would be mostly theoretical, because what we're going to be doing in this class is trying to explore other ML algorithms. So remember, we've introduced ML, and we introduced two basic algorithms, which are logistic and linear regression. So we've built on top of those algorithms and tried to lay foundation on some concepts, right? So, but there are still a lot of other ML algorithms that we are yet to look at. So we're just going to look at some of them, right, which you'll most likely be using in your project as well. So every other class from today till the last class we're going to be having would be necessary, will be very, very important for your project. So don't think that all what we've done so far is what you would be needing, only what you'll be needing for the project. No, we are not done with the with our curriculum yet. So it's basically work as you learn, right? So as you are learning, you are doing your project and just doing everything together. All right. So yeah, let's proceed. Let's proceed. So I don't know if I'm missing anything. Am I missing anything? So how is the project going so far? Like on your end, how is it going so far? Have anyone started the project yet? Has anyone? How is it going? Any problem? I've seen the issue about the Google Form stuff. That will be rectified. So that is basically for submission aspect. But I feel the link for the data set is already available. So yeah, that should get you started, right? Please, and what I'm going to advise you is that please don't slack on this, right? You actually have enough time, more than enough time to finish this project. So don't say because you have time, you're going to just wait till let's say the deadline draws near, and then you start the project thinking that you can like finish up with it in in a short space of time. Please don't do that. You're going to just shoot yourself in the leg. Please try as much as you can to start, whether it is just opening the data set, loading it, importing library, just start with something, right? So you don't get to put pressure on yourself towards the deadline. All right, so okay, great. All right, so I can see that most of us are already started with the projects. Some are cleaning the data set, exploring the data. That's fine. That's fine. So I don't know if I'm missing anything. Gideon and Nigeria, please, do you both have anything to say or anything to remind me of before we start class?
Good evening, sir.
Yeah, good evening, Nigeria. Welcome back to class. We've actually missed you. We're glad that you're back here with us.
Thank you very much, sir. I really do appreciate. I am back, well and strong. Thank you so much, sir.
All right.
So for now, nothing really on the table. Just a reminder to please record the class. And secondly, I don't know if Gideon will be able to talk now or not. His network is a bit unstable, so I don't know if he'll be able to talk now or not. But so far, so good. It's simply a reminder to record the class. Thank you, sir.
All right. Yeah. Thank you very much. So yeah, definitely. The class will be recorded because I'm expecting. I'm not expecting so much persons to be on this class because of the timing and all of that. So recording will be made available. I'll try as much as I can to push it out as soon as possible. All right, so great. So let's just move and start with what we have for today. Okay, so I believe I shared some materials. For this class. If you check the group, you're going to see week 11 session 22 and week 12 session 23 materials. All right, so these are the materials that we are going to be using for this class. If you already have it, but these are the two materials. We'll try to cover both of them in this class. That's the aim of this class, to cover all ML algorithms. Not all, like some of the other algorithms that we have to cover. All right, so there are a lot of ML algorithms that we possibly can't even cover everything in this short period of time. So we're going to do our best to just introduce some of them to you so you can have an understanding. All right, so now we're going to look at other machine learning algorithms. So as you can see on the screen, we have three of them here. We also have the second material here, which has some other algorithms as well. So this second material will focus solely or mainly on ensemble learning. All right, so I'm going to explain what ensemble learning is, but before we go there, you need to understand these ones that we have here. Now, these are not all the algorithms that you have, right? We also have some other algorithms, but these ones are like most common and most popular ones, and also the ones that some of the ones that you can find in Scikit-learn as well. So what we're going to do is just a kind of conceptual overview. Like we're going to touch on how they work, and we can just do a little demo, right? Just showing us how we can use it, which you are familiar with already, right? So the same process in which we import the class, the particular model class, and then we initialize a model object and do what we want to do, like including hyperparameters and all of that. The same thing we're going to do, right? But the main thing is just to understand how and when to use them, or basically how this model is working under the hood, like what is it doing and how is it doing things differently, right? So that's what we're going to be doing today. So let's just kick in. Now we're going to look at three other ML algorithms. We're going to look at KNN, we're going to look at support vector machine, and we're going to look at decision trees. All right. So these ML algorithms, basically, they are popularly or mostly or commonly known for classification tasks. All right. So, but they can be adapted for regression tasks as well. But they are mostly known for classification tasks. As I said before, that most of the ML tasks you're going to come in across would most likely be classification tasks. All right. That was. All right. Sorry, was it?
Sir. Just in case the screen is not showing, just in case.
The screen is not showing. Please, can someone else confirm if that's the case? Okay. All right. So let me just try. All right. So can you see the screen now? Has it come up?
Yes, sir. We can see the screen now. Thank you.
All right, great. Okay, so as I was saying, we're going to be looking at several ML algorithms today. We have two materials we will try to cover today. We have this where we're going to look at KNN, we're going to look at SVM, and we're going to look at decision trees. And we also have the second material where we're going to look at ensemble learning, which I kind of a family an algorithm that's algorithms basically that belong to a family, and we're going to try to explain and just differentiate them and how they differ from your regular ML algorithms. So we're going to start with this. We're going to start with KNN, and we're going to move on to SVM and decision trees. I was also saying that these models, these algorithms, they are mostly known for classification tasks, but they can be adapted to perform regression tasks as well. So most of the ML tasks you're going to be doing, like they are usually more of classifications task, right? So that was even one of the reasons why your project is a classification task, and it helps you to even have a better understanding of how to approach ML project, because the evaluation stage in classification task is kind of is more sophisticated and more complex than your the regression counterpart. So it's better you learn how to build or how to work with how to carry out ML projects with classification tasks. So most of this explanation would be focused on classification tasks. So just so you know. And yeah, so that's going to be that. Let's just start right away. So we have the first algorithm here, which is KNN. So we all know what an algorithm is, right? An algorithm is basically a process or a step-by-step process to performing a particular task or to like solving a particular problem. So when we come to machine learning, we have several algorithms, which basically means several approaches that you can take to achieve or perform a particular task. So in your project, I don't expect you to use a single algorithm for it. Like you're expected to try out different algorithms. Let me see how you're able to like test these algorithms on your data set, and also see the performance of each algorithm, and also like see how you're able to perform hyperparameter tuning as well, right? This hyperparameter tuning might sound strange to you, right? But we are going to have a dedicated class for that. So hyperparameter tuning, as I explained in the last class, is basically a way of fine-tuning some values, right? Some values that would help you get a very good model performance. So each algorithm has different hyperparameters. All right. So for KNN, you're not going to have the same hyperparameter for KNN as you would have for logistic regression, as you would have for linear regression, or as you would have for decision trees or support vector machines. So each algorithm differ in this aspect, right? They have different hyperparameters, right? So these hyperparameters are things that you also need to know, and things that you like, basically things that you need to know to ensure that you are tuning your ML model well enough and setting the right hyperparameter values to give you a very good performance, right? So that's basically the difference. One of the differences between these algorithms, they have different hyperparameters. So it will make more sense to you as we move on, right? But just keep this at the back of your mind if you can. So the first one we have here is KNN. Right, KNN is it's called K nearest neighbors. All right, so this is an algorithm that is also used for classification and regression tasks, as I said. But I'm going to first explain exactly how it is used for classification tasks, and from there you can just like explain how regression tasks can also be adapted from this particular algorithm. So KNN is a simple, intuitive, and versatile machine learning algorithm. So when you actually bring all the algorithms and you lay them side by side, or you just put them up there in a list, KNN should come up as the simplest algorithm, right? It actually comes up as the simplest algorithm. And there are some things I'm going to talk about KNN, and that would show you that this algorithm kind of differs from other algorithms. So remember when we talk about model training, where we said that for you to have a model, you have to expose your you have to actually show the machine basically your data, and the machine learns from that data using a particular algorithm and some many other things. But for KNN, it actually doesn't learn in that sense. And we're going to explain what it means. So KNN is usually called a lazy learner. Basically, it is called a lazy learner, L-E-Z-Y, lazy learner. So let's just move on with that. I think this will make more sense as we proceed. So as you can see on the screen, it can be used for both classification and regression tasks. Okay, it's a type of instance-based learning where the algorithm makes predictions based on the similarity between the input data and the stored instances in the training set. Right, so don't worry, we'll explain what this is. I'm just trying to just read out from what we have here. Okay, so the core idea of KNN is that are likely to have similar inputs. So let me just start with this. Whenever you hear of KNN, what should come to your mind is that birds of the same feather flocks together. All right. Whenever you hear KNN, what should come to your mind is birds of the same feather flocks together. That is the core idea of KNN. So it's just basically like seeing a group of you can identify a particular group of birds or a particular bird species, right? And you always see them flying together in groups, right? So there's now a particular bird that you really don't know, right? But because it's flocking together with those set of birds or that group of birds, you automatically or you assume that this bird that you don't know about or you've not identified belongs to this group. Okay, so you actually attach attributes to an unknown object based on its association. All right, so you attach an attribute or you classify that unknown object based on its association. So just the same thing as when someone says, "Show me your friend," and I will tell you who you are. Right, so some persons might not know you, all right, they don't know anything about you at all. But when they see your friends, when they see people that are around you and all of that, from there they can basically extrapolate and say, okay, because of what I am seeing, right, because of your association, I can deduce that this is who you are, right? So the deduction might be wrong, right? Might not necessarily be correct. So obviously, there's always an error whenever we talk about prediction or we are assuming or deducing something because we don't really know something for a fact. We're just using the data we are seeing to make or to come to a conclusion. So this is the key idea in KNN. We are trying to label an object that you don't know based on its own association. That is basically how KNN works. That is how it makes its prediction. All right. So remember in logistic regression, we talked about how logistic regression does its own prediction. And can someone just remind us of the key idea or the key concept that makes logistic regression works or that helps in prediction and in prediction for logistic regression? Like the core concept in logistic regression that makes it logistic regression. Can someone just remind us of that particular concept? Okay, I'm just going to, I won't really expect much responses because of the number of persons in class, but yeah, so it's using the sigmoid function basically. So sigmoid function is what is the key idea in logistic regression. So these are the things you need to know as a data scientist, all right? So when you come to an interview, when you are like searching for a job and all of that, trust me, before you go ahead to like start writing code and all of that, they would try to drill you to know or to be sure that you understand what you are doing. Okay. So the reason why you're a data scientist is because you have you understand how these things work. You don't just know how to write them in code. You understand how they work. So it's very essential that you know these things. Like very, very, very important. Okay. So you should always associate sigmoid function with logistic regression. And then when you come to KNN, you're going to like you should also understand the key idea or the core concept in KNN. So as you can see on the screen here, we have data points, right? Represented. We have a chart representation of data points. So in this particular chart, we have two groups. So you're going to consider these two groups, the two colored groups, basically the red and the blue. So you're going to consider these two colored groups as the classes that you are working with. Right? Let's just say your data set, you have two classes, a binary classification tags. You have two classes, and you're trying to create a model that would help or that should be able to make predictions or that should be able to predict those two classes based on the data that you have. All right. So let's just use this as a visualization of how KNN works. So when you represent the classes on your data set, in this case, you have just obviously it is just a two-dimensional data set where you have just two features. So that's just why you have it like this. In reality, you might have more than two features, like let's say 10 features. So it will be more difficult to represent a 10-dimensional data in a graph. So we use the simplest form, which is two dimensions. So you basically have two of them, one in the y and one in the x-axis, and then the data points are classified, right? Based on the classes in which each of them belong. So now, in this case, let's assume you have a new data point, right, that you want to predict. In this case, this green data point here is what you want to predict, basically. So the way KNN works is that it looks at the surrounding data points here around it and picks for classification tasks. It looks at the immediate data point, and we're going to see how we can like determine the number of data points to look at to make its classification. But in KNN, the notation we use is neighbors. We use neighbors. So it looks at the nearest neighbors. That's why we call it K nearest neighbor. K stands for the number of neighbors. Nearest, you know what nearest is, and then neighbors are the closest data point here. So let's say while building your model, you choose to use 4 neighbors. All right. So your K in this case will be 4. So you choose to use 4 neighbors. What your model will do, or what the algorithm will do basically, is to look at the closest 4 neighbors. So in this case, we want to like classify this unknown data points here. So by using K equals to 4, our model will look at our algorithm, or our model basically will look at the 4 closest neighbor here. So in this case, if you can count the 4 closest neighbors, you will see that 4 of them belong to this blue class here. So automatically, the highest number of class is going to be the one assigned to this new data point. So after your prediction, this green dot here is going to become blue. All right. So that's how we have, or that's how KNN makes its prediction, or that's how KNN works. There is no training being done. You are not learning anything basically. You are not learning parameters as you do when you are like building logistic regression, right? It just tries to it just represents the data points, right? And then it uses distance metrics, right, to calculate the distance between the data point you're trying to predict and the closest data points here. Okay, so this is the core idea, is the key idea in explained in a very simple way. So there are actually some things that like are technical when it comes to KNN, but this is the key idea of KNN. So let's just say you also want to like select another key, right? You want to, let's say, increase your K from 4 to 9. So you want to use more neighbors in your classification. So it is obviously going to expand its reach to cover 9 neighbors. So when it calculates the nearest 9 neighbors, it then looks at each of those nearest 9 neighbors and count the number for each of them. So in this case, we'll see that we have this 9, right? This dotted dash, right? This dash that we have on the outside, we have, out of all the 9 neighbors, we have 5 of the red neighbors, and then we have just 4 of the blue neighbors. So given this K that we have here, which is equals to 9, what class will this unknown data point be assigned to based on this new K that we have now? So I need a response. Let me know if we actually understand what I just explained now. Exactly. So our KNN algorithm looks at the nearest 9 neighbors and counts the number of classes on each side. And then the class with the highest number is going to be the class that the unknown data point would be assigned to. As you can see how simple that is. So that's why I said birds that flock, how do they even put it? Like, based on your association, you are going to you can be identified, or the attributes of a particular group can be assigned to a particular person based on the association. All right. So that is how KNN works. So depending on your K, you're going to have a different result. So K now in this case is what we call hyperparameter. Right. So remember I told you that different algorithms have different hyperparameters. So for KNN, your K in this case is hyperparameter. So you can actually tune your K. You can change the value of your K. If you change the value of your K from 4 to 9, you see that the prediction will change, right? So you need to understand, or there are things that you need to know before selecting K, okay? So that is how KNN works. So let's just move on to the more technical stuff. Now, everything I've been explaining is highlighted here. So how exactly does KNN work? First of all, you choose your K, right? So first thing is that the number of K is choosing, which is your hyperparameter. So if you just read here, you see that K here is a hyperparameter that determines how many neighboring points will influence the classification or prediction of a new instance. Okay, so remember I told you a hyperparameter is a value that can influence the performance of your model. So if you change your hyperparameter from a particular value to another value, it can actually make your model better or make it worse. So you have to actually know how to tune hyperparameters. All right. So there's a particular class that will be dedicated to that. I think that should be this week, Saturday or Sunday. If not, it should be our last. So our last class is going to be in 2 weeks. So after this week class, we're going to be having our last class next upper week, right? So after that, then we're just going to have our presentation and then conclude. So I don't know if I've told us about our presentation. So our presentation is usually done at the end of every cohort. So those that came, we can't actually take every single presentation. So the way we do it is that the top end performance will be selected, and then they'll be given the floor to present their project, explaining what they did and all of that. So anyways, I'm going to talk more on that in our class on Saturday or Sunday. So after you've chosen your K, you're also going to choose what we call distance metric. Okay, so a distance metric is used to measure the similarity between instances. So remember I told you that what your KNN is trying to do is trying to get the nearest neighbors. So how does it determine those data points that are closest to it? It is via distance metric. So we have several distance metric. We have Euclidean distance, right? We have Manhattan distance. We have Minkowski distance. So these are the most common ones. The one you mostly be using is your Euclidean distance or Manhattan distance. So this is what we call distance metric. So it's what determines the distance between your new or the unknown data point and the closest data point, right? So after that, it is also going to this is how it finds your neighbor, right? So in this case, for a given input instance, the algorithm calculates the distance of to all instances in the training set. So this is what KNN does. Instead of training and learning and calculating errors and all of that, it just calculates the distance of all the instances. So that's what takes up computation for KNN, distance calculation. All right. So if you have like 10,000 observations or 10,000 instances, it calculates the distances between the data points to be predicted and all other data points that you have there. So it now ranks them, right? So from nearest to farthest, and then based on the key that you selected, it will now just select those number or the nearest ones, the k nearest ones, and then like calculate the class in which each of those data points belong to, get the highest class, and assign the newest or the one that you want to predict, the unknown data points, to that class with the highest number of data points. So that is how KNN works. So you have to choose your K here, right? You then choose your distance metric, and then this happens, and that is basically it. There is really nothing more that's been done when it comes to KNN. So you can it can be adapted to regression as well. So for classification, the class label is assigned based on the majority vote among k neighbors. So this is what I've been explaining since. So when you calculate, when you get the k, the nearest k, then you now calculate or count the number of classes that you have in that the nearest neighbor, and the class with the highest vote would be the one that, or would be the label that will be assigned to your new data point. So that is how prediction is being done in KNN. For regression task, remember in regression, we are trying to predict a continuous value. So it's usually numerical variable. So for continuous variable, when you still have to select number of k for regression task. But in this case, what is going to be calculated is the average. So if you say k equals to 5, it's going to get the nearest, the top 5 nearest neighbors, all right, and calculate the average. So in this case, the nearest neighbors would be different values, right? So you can say, let's assume you're trying to predict, let's say the price of house, a price of house, and then you have several features. So let's say the range of these houses are usually from, let's say, let's use dollars. Let's say from $100,000 to, let's say, $900,000. All right. So your k, or the nearest neighbors that you'd have, would be any value between these two values. So once it gets that nearest k, that k nearest neighbors, it then gets the average. And then the average of those k nearest neighbors would now be your prediction. So if you use k equal to, let's say, 3, right, the average you're going to get will be different from the average you're going to get when you use k equals to 5, right? So you can now see how k affects your predictions. You can now see how k is a hyperparameter that can be used to. So when we talk about hyperparameter, we'll see how to actually train our model based on different keys. So we'll train a model when our k is equals to 3, train a model when our k is equals to 4, 5, 6, 7. So for each of those k, we're going to get a model performance, and then from there we can now see, okay, this k is the one that will give us the best performance, and then we can now select this k. That is what we call hyperparameter tuning, all right? Trying out different values, trying out different hyperparameter values to see which of the value would give us the best, performance, all right? So there are some key points to note for KNN. So KNN is a lazy learner, right? It's a lazy learner basically. because it does not explicitly learn a model. Right, this is what I've explained already. Like, it does not learn a model the same way linear regression learns a model. Remember, linear regression, learning basically is like trying to map out relationships between input and output, and then you try it for the first time, you compare it to what you already have, and then there's an error, and so you use that error to improve on yourself and go again, map out the relationship based on your updated parameters, and then you compare it to the original labels, and then you see that, okay, there's still an error. So what you're trying to do during learning is to try to minimize error, right? So during machine learning, during training in machine learning, what you are basically doing, you are minimizing the error. And in supervised learning, you are minimizing the error between the predicted values and the true values, right? So the training data set has your label. So everything that is being done is being compared with that label, and then a cost function is computed. So I don't want to go into all those mathematical stuff, right? Because there's a lot of mathematical stuff that goes into training a model. So we have gradient descent, which uses some mathematical concept like calculus to calculate our loss function and all of that. So, but in summary, what is being done during training is that we are trying to minimize the error between the prediction made by that model and the actual value. So this kind of learning is not replicated or is not done in KNN. KNN basically just calculates the distance, right, and get the top n neighbors based on your hyperparameter k, and then just use it to classify or assign a label to the particular data point you're trying to predict, or whatever it is you're trying to predict. It just gives it a label. If it's for regression, it gets the average and assign that average value as your new prediction. Okay, so it's a lazy learner, and that I just explained what I mean by lazy learner. And we also have this other point here. It is non-parametric. So KNN doesn't make any assumptions about your underlying data distribution. Remember, in linear regression, we actually looked at some assumptions that your data has to meet before it works, before it will actually give you like a very reliable stuff. But KNN, it doesn't. It's good to go. It works with every data. It's flexible, basically, right? But something about KNN is that whenever the features of your data set increase, the performance decreases, basically, right? KNN can perform poorly in high dimensional space. So whenever you hear anything like high dimensional or dimensional, basically in machine learning, what we mean is the number of features, or what we are referring to are the number of features. So when we say something is high dimensional, it basically means that it has a lot of features. Let's say that your particular data set has like 100 features, which is actually possible. So it is a high dimensional data. So KNN can perform poorly in a high dimensional space because the distance between points increases, making the concept of closeness less meaningful. So if you actually translate what I've explained so far into a situation where you have a lot of features, calculating the distance becomes tricky, all right? Because that's the main thing that is being done in KNN. So calculating the distance in a high dimensional data set becomes very tricky, and then it begins to lose its performance, and you'll really not be able to make a good model or build a good model using KNN for high dimensional data. So if you're working on small data sets, KNN is good. It's actually going to give you a very good, a decent performance, right? But it's not the best model out there, but it's a model that you need to know as well. So you can see we have illustrations just explaining what we just talked about. You can see, like in this case, we have a two-dimensional data set. X1 is on the x-axis and X2 is on the y-axis, right? So this is a two-dimensional data set. If it's a three-dimensional data set, we're going to have so if it's a three-dimensional data set, we're going to have another axis basically. We're going to have X3, and then this representation is going to be in in 3D basically. So there's something about machine learning. You need to understand dimensions when it comes to machine learning. So when it comes to visualization, right, you can only the highest dimension you can visualize is 3 dimension. So outside of 3 dimension or higher than 3 dimension, you can't have that kind of representation. You can't represent any dimension that is greater than 3 dimension in a visual format. All right. So we can only explain it conceptually so you understand. So whenever we are explaining any concept or technique, we try to use 2-dimensional visualization to explain it to you. But in practice, features we use are usually more than 2 dimensions. They are more than 10 dimensions, 15 dimensions, and all of that. So now I've introduced another new notation, which is dimension. So dimension in ML is the same thing. When we talk about ML, we're also talking about features, right? So each feature corresponds to a single dimension. Each variable, each X variable corresponds to a dimension. So if you have 10 features in your data set, that data set it has 10 dimensions basically. So if you're trying to represent it, it's going to have 10 dimensions. So it doesn't even, like, you can't even wrap your head around 10 dimensions. So that's why we talked about this cost of dimensionality here. That would be the higher dimension you have, the more difficult it is for KNN to actually make a meaningful and create a meaningful model. So in this diagram or this chart we have, you can see that we're trying to predict this new data points here. All right, so this is the prediction phase. The training phase or pseudo training phase, as KNN doesn't have a training phase, is the calculation of metrics, right? The distance metrics and all of, or just representing the data points basically in a high dimensional space. That's the training point. The prediction stage is where the actual stuff happens. It is where the distance metric is being calculated. All right. So for this blue dot we have here, so once we want to like classify this blue dot to green or yellow, what happens is that KNN calculates it uses a particular distance metric to calculate the distance between this blue dot and this one, between this blue dot and this one, between this blue dot. So it does it for every data point. So in this case, we have just 2 data points, right? But in reality, we have a lot. We have like 1,000, 10,000, like a lot sometimes. I think in the data sets, I don't know I've forgotten how many data points you have in the data set I sent for your project, but just imagine representing that number of data points on a graph like this, on a scatter plot like this, right? You understand what I'm saying. So each data point distance will be calculated, and then the K you choose would now determine the focus of your model, or the particular number or the particular area in which to be focusing on. So in this case, because let's just assume we are choosing K equals to 3. All right. So in this case, we are going to select the 3 closest data points. So it's going to be these 2 here. Let's just assume, because we don't have an exact value, let's just say this 2 green one and then this 1 yellow one here. So if K is equal to 3 and this particular area is the area of the 3 data points, based on this, our new data point, our new prediction is going to be in the green category, right? Because the green data points have the highest number of vote, quote unquote, right? We have 2 of the green one and 1 of the yellow one. So automatically it will be assigned to this green one. So that's how it works. That is how KNN works. So let's not dwell more on that. Let's just move ahead to the next thing. So implementation is very easy, right? So what you do is just import KNN from neighbors. Let me see if I can open a notebook. So as I said, this class is mostly going to be focused on explaining the theoretical aspect. We're not going to do much implementation. So to import your KNN class, what you do is just go to import Scikit-learn from Scikit-learn, rather, not import Scikit-learn, from Scikit-learn.neighbors, import KN classifier. So let me just confirm. So we'll import K-neighbor classifier. K-neighbor classifier, right? This is okay, there's no U here. So now the K-neighbor classifier class here is going to be used for classification tasks. Okay. Why K-neighbor regressor is going to be used for regression tasks. The regressor. So these are the classes that you're going to be using to build your KNN model. You can use KNN classifiers. I think. Let me just copy it. Alright. So if you import it, you will see that the classifier object here can only be used for classification task, while the regressor object here can only be used for regression task. So depending on the task that you're given, you import it out of them. So for classification task, you can see here that we have a hyperparameter n neighbors. All right, and you can see that we have the metric here. So the metric in this case is the distance metric we're going to use. So if you just scroll down a little, you're going to see that we have several distance metric. So where is that? So you can see that a metric to use for distance computation, and the default is Minkowski. So Minkowski is the default. So if you don't indicate any metric, it's going to result to using Minkowski, right? So you can actually set it to other metrics as well. So as I said, we have Euclidean distance, and you also have Manhattan distance. So you can see it here, Manhattan distance here, and you have Euclidean distance. So a lot of things to do. So all these things that you have here, all these parameters you have here, they are called hyperparameters, and you can tune them to change the performance of your model, right? So you just have to understand what you are doing first, right? You just have to understand why you want to do this particular thing. So if you are starting out, you just start out without doing anything. Just leave the default, they let them run, and then you can just iterate from there. So if you want to use your KNN, you can just come here and say KNN classifier, and then you just say KN neighbors classifier, and then by default your n neighbors is 5, so you can change it if you want, but by default the number of neighbors is usually 5, so you can change it to and your neighbors value should obviously it should be an even number, because if you're doing majority voting, you always should have unequal distribution. So if you put an even number, you can see the kind of problem that you would have. Possibly you have 2 of the classes belonging. You can have 2 of each of the classes in, let's say, when you indicate n neighbor equals to 4. So and it's going to be an issue. So you also always have either 3, 5, 7, 9, and so forth. So for the acceptable range, or the most commonly used range, usually either 3 or 5. All right, but sometimes you can use 7. But anyways, when we look at how we can tune hyperparameters, you don't have to disturb yourself with choosing a particular value, because you can just use grid search to search through the particular hyperparameter value that will give you the best result. All right, so this is just how you can use your KNN. So once you've created your model object, you can now come here and say KNN, and so once you choose it, you can just use your fit object to. The thing, this is just for props basically. It's not really fitting anything. So when you fit it, it does what it's doing, and then you can now make your predictions. So that's just how KNN works, right? So you can now evaluate your model with the same evaluation techniques that we've learned about. So every other thing aside the model itself and the hyperparameter stuff, every other thing are the same throughout, right? So it's the same for every kind of model. Like for classification models, it's the same. For regression model, they are the same. All right. So in conclusion, KNN is a straightforward and effective algorithm for both classification and regression. And I said before, it is particularly good for small data sets with well-defined clusters. Its simplicity and ease of implementation make it a popular choice, though it can struggle with high-dimensional data and large data sets due to its computational complexity. So just so you know, that is it for KNN. I believe that is actually straightforward, and you've understood exactly how it works. So we're going to look at another algorithm called support vector machine. Okay, support vector machine. So this algorithm is another very interesting algorithm that can be used for classification tasks and can also be used for regression tasks. So I'm actually not going to dwell more on the regression aspect. I'm just going to explain the classification aspect of it, because there are a lot of stuff to talk about in the classification aspect. So and you mostly use it for classification tasks. You barely use it for regression tasks, right? So let's just move on. So support vector machine, we also call SVM. They are powerful supervised. Everything we are looking at today are their supervised models, right? So they are supervised models. So they are used for classification and regression tasks. So now, this following explanation is for the classification task, right? So the task type will determine how the algorithm works. So by default, although they have support vector classifier and support vector regressor as well, but it is commonly known for classification tasks. So what SVM does, the core of SVM is that it wants to find an optimal hyperplane. So that is basically what it is trying to do. So these are the things I need you to remember. Well, even if you forget every other thing, which might be expected sometime because of the number of stuff to learn and all of that. So if you have to forget every other thing surrounding an algorithm, don't forget the key idea or the core idea there. So for linear regression, you know that the core idea in linear regression is trying to find the line of best fit. Okay? It's trying to find the line of best fit, basically. And for logistic regression, it's the same idea with linear regression, but now it is introducing sigmoid function that will basically convert the numerical predictions to a categorical prediction based on the number of classes we have. Then for KNN, you already understand how it does its stuff by like classifying a particular data point based on the number of neighbors around surrounding it. Okay. Now for SVM tries to find the optimal hyperplane. Now you might be wondering, what exactly is hyperplane? Which one is all these strange concept or strange words that we're just introducing this night? So this is going to be very, very like common. You're going to be hearing a lot of new stuff, right? Especially when you even go into the advanced aspect of ML, so you should actually be comfortable with learning new concepts. Okay, so all these small concepts that sound somehow, they're actually the key to understanding a particular thing. So once you understand what a hyperplane is, I think you'll get an idea of what support vector machine does, right? So let me just go ahead with you. So SVM basically tries to find the optimal hyperplane that best separates data points of different classes in the feature space. Now this sounds like one kind complex stuff, but let's just break it down and see what it means. So let me repeat this again. So the core idea of SVM is to find the optimal. Now, optimal in this case means that there are different hyperplanes. You can actually have so many hyperplanes, but what SVM tries to do is to find the optimal one. Okay. So now we have hyperplane. What exactly is hyperplane? Hyperplane, as you can see here, is a plane of lower dimension. Okay, let's just say that in your feature space. Now, what we call feature space is an imaginary space where all your features are represented. Okay, so in this space now, in this case where we have this particular chart, this is our feature space. So don't allow all this thing I'm saying confuse you, right? They're just like technical terms for simple stuff. That technical terms that sound complex, but they actually are trying to explain a simple concept. So this is a feature space. A feature space is where all your features are being represented or are being projected. Okay, so that is why we try to use visualization sometimes to explain some of these things, because everything that happens, they're happening in a feature space, right? They're happening in an n-dimensional space. N-dimensional space meaning, let's say you have 10. If you're working or your algorithm is going to be like doing anything, it's going to be doing that stuff in that 10-dimensional space. So if you have 15 features, it's going to be a 15-dimensional space. So a 15-dimensional feature space. So that's where all the stuff that is happening or all the things that your algorithm is doing is going to take place, will take place basically. So this is a feature space, so you don't get confused. Let's just move on to what we explained now. As I said, a hyperplane is a lower dimension, a dimension that is lower than your original dimension. So your original dimension or your n dimension in this case is number of features you have. Your hyperplane is going to be a dimension lower than your n dimension. Right? So your n dimension is the number of features you have. So your hyperplane is going to be, if you have a 10-dimensional data set, how many dimensions will your hyperplane be in this case? Based on the explanation I just gave, if you're having, let's say, a data set that has 10 features, how many dimensions would the hyperplane be? Okay, I'm waiting for more responses. Okay, so let me just go back. Let me just explain it again, because this might be new to you. We are actually getting it. If you say 9, you are correct. That is exactly the dimension of your hyperplane. So in a case where you have two-dimensional data sets, you just have two features. Your hyperplane is going to be just a line, right? Because a dimension lower than 2 dimensions is what? A line. Now, if you have a background in is it geometry, I think this is going to like be easier for you to understand. So when you have a 2-dimensional space, the hyperplane in that space is a line. So you are trying to find a hyperplane that best separates your classes, right? So you are trying to find a line. Right, let me go back to this particular case. So let me see. I wish I can draw my screen, right? But let's just try to illustrate it with this. So let's just assume these are our data points now. Like this is a two-dimensional data point, right? This is a two-dimensional feature space. So you have two of your features here represented here. Now, the hyperplane in this particular feature space is going to be a line. So what SVM is trying to do in this particular case is trying to find a hyperplane that best separates these two classes. Okay, so let's just assume this particular, if you see my cursor now, see where it's starting. So let's just assume this particular separation here is the best hyperplane. So this is going to be your model. So this hyperplane here will separate the two classes. So the hyperplane in this two dimensions is a line. It's very straightforward, very simple. Now let's add one more dimension to our data set. If we now have three-dimensional data set, that is three features, our feature space is going to be three-dimension, then our hyperplane is going to be in two dimensions. So our hyperplane is going to be a plane. Okay, a plane basically is a two-dimensional object. Now, as I said, these are some geometrical concepts which might not fall easy on some of us, but just try to follow me here. If you don't get it now, fine. You can always go back and look at this and hear the explanation or look at what I'm explaining. So in three dimensions, the hyperplane is a plane. So a plane is a two-dimensional object. So you're trying to find a two-dimensional plane that can best separate your three-dimensional data into the different classes. Okay, so some of these things might be difficult to visualize as we are climbing up in visualization. So in a four-dimensional feature space, so you have four-dimensional features, your hyperplane will be a three-dimensional plane. So it will be a three-dimensional hyperplane, right? Because now a plane is a two-dimensional stuff, so you have to call it hyperplane. Hyperplane in this case is when it is more than 3 dimensions. Okay, so your hyperplane in a case where you have 4-dimensional features would be 3 dimensions. So you are going to use a 3-dimensional hyperplane to separate your data, to separate the classes of those data. All right. So now that is the idea behind SVM, is trying to find the hyperplane that find the optimal hyperplane that best separates data points of different classes. Remember that you are trying to make predictions. So you want to create a hyperplane, like say, okay, all the data points that are on this side of the hyperplane belong to this class, and all the data that are on this side of the hyperplane belongs to the other class. All right. So depending on the dimension you are working with, that particular hyperplane will do the work of separation. So once that hyperplane is created, your prediction can be done. So once you have a particular data point, that particular portion of the hyperplane where that new data set falls in is going to be the prediction. So if it falls in on the side of the hyperplane that has class 1, then that particular data point will be classified as class 1. If it falls in on the other side of the hyperplane that is class 0, the predicted value of that data point will be class 0. So the main thing is to find that hyperplane first. Once the hyperplane is created, then your prediction can be done. All right. So the training in SVM is trying to find the optimal hyperplane. Right. So I'm just trying to build the foundation. We still have some other things to talk about. Now, there are some key concepts in SVM that we need to talk about. So the first one is hyperplane, which I'm trying to explain. The second one is support vectors, which I will explain. Third one is margin. Fourth one is kernel trick. All right. So these are the 4 key concepts in SVM: hyperplane, support vectors, margin, and kernel trick. So I will explain that, but let me see that I think there's a visualization here that kind of explains it. So now I know I'm still coming to this, right? But I just think I should use this to explain hyperplanes for you. So in this case now, in this scenario, this feature space we have here is how many dimensions? Let me just see if we understand what I'm trying to explain. This feature space here that I'm moving my cursor on is how many dimensions? Is of how many dimensions? Thank you very much. This is of 3 dimensions. right? This basically represents the number of features we have, right? So we have, in this case, we have just 3 features. So when we try to represent them in visuals, we are going to be seeing something like this, a 3-dimensional object that has our data points scattered all around it, all right? So now you can see this blue stuff here. This blue stuff here is what we call a hyperplane. So this hyperplane is inside that 3-dimensional object, okay? And it's always of 1 dimension lower than our original or our feature space dimension. All right. So it is this plane that we have here is a 2-dimensional hyperplane. So this is what now is used to separate the classes. All right. This is what we use to separate the classes basically. So once the hyperplane has been created, then we have our model. That is our model basically. So the model is us trying to get an hyperplane, a hyperplane that best separates our classes. All right. So this can be difficult to understand at the first explanation, right? But trust me, it's not really complex like that. I know I'm saying it from a higher standpoint, but it's actually not so complex. So let's just move on. So we have support vector. So support vectors in this case, they are the data points that are closest to the hyperplane. So to create the hyperplane, there are some things that your SVM algorithm are going to look at. So the support vectors are one of them. So these are data points that are closest to the hyperplane. They play a crucial role in defining the position and orientation of the hyperplane. Like, I really wish there's a way I can project the visuals from my head to your head so you understand perfectly. But I'll try my best. I'll try as best as possible to just bring this to life. So now, support vectors now are one of those things. Remember, the algorithm we have now is support vector machine. So support vector in that case, they are the data points that are used to create these hyperplanes. So this is a 2-dimensional. This is a 2-dimensional feature space, right? It just has 2 dimensions, x and y axis. All right. So now we have the hyperplane that has been created here. So in between these 3, among these 3 lines here, which one is the hyperplane? I want us to just figure this out with me. Among these 3 lines here, which one is the hyperplane? Exactly. So this is the hyperplane. To create this hyperplane, there's something that is going to be considered first, which are called support vectors. So all the data points that we have here, all of them, they are called vectors. All right, they are vectors. So now the support vectors are those vectors that will be closest to the hyperplane. They are the one on the outermost, just like the ones on the boundary, right? So after the boundary, you are not going to see any other person. So those people that live on the boundary, they are called the support vectors, right? So they're the one that will determine how the hyperplane will be created, right? So that is what support vectors are, right? I just wanted to explain that to you so you understand. So support vectors, they are data points that are closest to the hyperplane, and they play a crucial role in defining the position and orientation of the hyperplane, all right? So now we have the third concept here, which is called the margin, right? So the margin is the distance between the hyperplane and the closest data point from either class. All right. So let me come again. The margin is the distance between the hyperplane and the closest data point from each class. So in this case now, this is our margin. This is our margin, right? So the distance between this particular support vector from this particular class and the hyperplane is a margin. And the distance between the support vector of this other class from here to the hyperplane is another margin. So what SVM is trying to do is that SVM tries to maximize this margin. So the higher the margin, the higher the separation, or the good the separation. Okay. So if you have a lower margin, that means the 2 classes are not well separated. So what SVM wants to do is want to try to maximize the margin so that the difference between the 2 classes will be high enough so we can easily distinguish between the classes. So this is the key idea in SVM basically, right? So it tries to maximize this margin. So if you understand this key point, you're going to Nigeria, data points don't get new name, vectors. See, that's one thing about data science. I think when I told us, when I was introducing this thing to us, I told us that to succeed in this field, you have to be open to learning. All right, you have to be curious enough to learn. So if you're someone that you're not really comfortable with learning, it's not going to, you are not going to actually thrive in this field. You have to be a person that wants to learn. You want to understand things. Like you're literally happy when you learn things, right? So you're literally going to enjoy tech field generally, because everything is all about learning new stuff and all of that. All right. So so this is basically what SVM does. It tries to maximize the margin so when the highest possible margin, the highest possible separation is gotten on margin, then you have your model. So you can now use that particular model with a hyperplane and margin and everything to start making predictions. All right. So that is basically what it does. Now let's move on to the last concept in SVM here, which is called kernel trick. Now, if you don't understand everything I've said so far, understanding this kernel trick will be actually much more tricky, right? So I want to believe that you kind of have an idea, right? You might not 100% understand everything, but you already have an idea of what I've explained so far as regarding SVM. So kernel trick in this case is a way to adapt SVM to classify non-linear data. Remember, I've already explained to you what linear data is, right? Whenever you're talking about anything being linear, you are talking about something being in a straight line. So if a particular data set can be linearly separated, all right. So let me just track back a little bit. We can have linear classification and we can have non-linear classifications. Okay. So linear classifications are those classifications, like for example, this one I just showed you now is a linear classification. Why? Why do we call it a linear classification? Can someone help us with that? Why do you think we call this one that is on the screen now linear classification? Thank you, Nigeria. It can be separated by a straight line, okay? So the reason why we call it linear classification is because it can be separated by a straight line. That is as simple as that. But there are some classification tasks or classification problems that you can't easily separate it with a straight line, right? The classes are not linearly separable. So for example, now in this case, you can see that when you represent the data points in a feature space, there will some set of this thing will be on one side. And so that is actually a very, very easy classification task to do. But most times, right, you would have non-linear separable data in the sense that some of these red vectors here would be in this place, and some of the lemon vector or whatever would be in this place. So they'll be kind of mixed together. So for you to use a straight line, it's not even possible. You can't actually even use a straight line to separate that kind of data. All right. So now there is a trick that is being done or that can be done to separate those non-linear data or non-linear classifications. So that's what we're trying to explain here, and it is called kernel trick. So kernel trick, there are different kinds of kernels that you can use to adapt your SVM to work with non-linear data, right? So SVM can handle non-linear classification by applying a kernel function, which maps the input features into a higher dimensional space where a linear separator can be found. Now, this thing is really not easy to understand. Like, I'm going to tell you the truth, right? So if you're understanding it now as I'm explaining it, trust me, like you are part of a minority, right? So this is quite a tricky concept, but I'll try to explain it as best as I can. So when you have non-linear separable data, what kernel trick does is that, or what this kernel trick I'm trying to explain does that it projects your data your data points from a particular dimension, from that dimension that it is currently in, to a higher dimension. All right. So as it is doing that, it's basically stretching your data to a point where you can now use a linear separator to separate the classes. I don't know if that makes sense. So it just transforms your data from a lower dimension to another dimension. So you can use a linear separator. You are not, in the actual sense, you are still using a linear separator for that classification. But what you are doing is that you are making it easier for that linear separator to be used by applying a KNN trick. So a KNN trick just projects the data points from a lower dimension to a higher dimension. So you can just apply that linear separator, and then you can have your hyperplane separating the classes. All right. So that is basically what KNN trick does. And KNN trick are of different types. We have linear KNN, we have polynomial KNN, and we have this radial basis function KNN. We have sigmoid KNN. So this, you don't need to understand how this KNN works, right? So at this point, you are not doing PhD thesis or whatever in machine learning. So you don't need to understand exactly how these things work. But maybe if you have time, it's not going to be bad to understand them. But these are the different KNN functions you can use, right? So the most commonly used one is your RBF KNN, right? So this one is used for non-linear data. So your linear KNN, of course, is the one that is used for linear data. So when you're working with linear data, you just use your linear KNN. But when you're working with non-linear data, you use RBF, basically. So all these things that I'm explaining, you can't actually see them, right? The only way you know what to do is based on the performance of your data, right? If based on the performance of your model, if your model is performing well, then I think what you're doing is fine. But if it's not performing well, then you cannot use the knowledge of all these things. All these things I'm explaining now is what will now help you, what will help inform your choice of what to use, or of what hyperparameter to tune, or what to change in your model. All right. So that's basically it. Now let's move on to how okay, for this KNN trick here, let me just show you the visuals. So this thing is this what I used to explain hyperplane is exactly what KNN trick is all about. So let's just say you have a two-dimensional data. Now this data set you have is a two-dimensional data. You can see that this data set is different from this one that we have here. This both of them are two-dimensional data, but this one is easier to separate this one with a straight line, but it's not easy to separate this one with a straight line. Like, how will you now start drawing this straight line? So you can see that the two classes, they are not linearly separable. All right, so this is where you now try to apply your KNN trick. So what the KNN trick does is that it converts this two-dimensional data. Nigeria, you go draw circle. The circle is no longer a straight line now, you understand? So anyways, let's just move on. So now this is your two-dimensional linear data, but then when your KNN is applied, it transforms this two-dimensional data to a three-dimensional data in a way. So it basically stretches them out so that you can now slip in a linear hyperplane into the data. So you can see that now these red classes have been stretched because of the new dimension. And so there's a way we can now separate both of them using a hyperplane. So we can now separate them, and then if you project them back to the two dimension, we're going to see that this hyperplane is going to be in form of a circle. But this circle is not what is there originally. It is this hyperplane that we have here. So this is just what this is what KNN trick is all about. So when you have a data set that is not linearly separable, you're going to go through this process. But if it is linearly separable, fine. There's no need to go through all this process I just explained now. I hope that is actually clear. So you can see this first diagram is two-dimensional non-linear training data. This one is a 3D mapped data point using Gaussian KNN and separating hyperplane. And then this is non-linear SVM with the Gaussian KNN. So all these things are just trying to explain how to apply KNN trick. So this is really some visualizations on linearly separable data, which you can see here. A single line can separate them, but non-linearly separable data is something you can separate with a line. So you have to apply KNN trick to this particular data set so you can have a good hyperplane. All right, so that is just how it is. That is as simple as that. So implementing SVM in SVM is actually very straightforward. You import as usual, right? You import SVM. So let me just see if we can import it. All right, so you just import. We have a module for it, which is SVM module. All right, let's see. So you say from Scikit-learn.svm import SVC. This is for classification. For Scikit-learn.svm import SVR. Okay, so SVR and SVC, they are still support vector machine, but the concept differs, right? So the one I just explained now is for classification task. So regression task follows a different approach, which I'm not going to explain in this class because we're not going to. It's not just SVM we are doing. We have other algorithms to look at. So we're just going to see how to implement. So this is for regression task, and this is for classification task. Okay, so once you import them, you can just easily come here and just say SVM model, and you say SVC. Okay, I've not run this yet. So you check on this SVC here, you're going to see the hyperparameters here. All right. So you can see the hyperparameters. We have a lot of them. You see the kernel here that I was talking about. This is the kernel, and the default kernel here is RBF, right? So RBF is a very good kernel because it's adaptable. So if you are working on linearly separable data, it will work. If you are working on non-linearly separable data, it will still work. So by default, they just made it RBF. So you don't need to stress yourself. So most likely your SVC, your support vector machine classification algorithm would work regardless of whether your data point is linearly separable or non-linearly separable. So this is the default. So I told you that Scikit-learn has actually made a lot of all these things easy for you. So with all this knowledge you have now, like you can now know why we have RBF here, right? So you can know some of these things. So there are a lot of other stuff here that we can tune. So when we get to hyperparameter tuning, we can just look at some of them. But most times you don't even have to touch most of these things. There's just few of them that you just touch, right? So in this case, the kernel is the one that you most likely tune. Sometimes you can, if you're working with a linearly separable data and you know it's linearly separable, just put linear there. So if you go to kernel here, this is how we have different options. We have linear, we have polynomial, we have RBF, we have sigmoid. Okay, so if you're working with a non-linear data, just use linear. It will work very well. All right, but if you're working with non-linearly separable data, then you can use RBF. So these are just how to use your SVC classifier. So for SVR is for regression. So regression is almost. I'm going to just send you a video to explain the regression algorithm basically, right? But you still have similar hyperparameters here, and you can just read them and see how they work. So you just come in and just SVC. I say kernel. If you want to use linear kernel, you can just put linear kernel here, and then say svm.fit svm model.fit, and then you can have extra the same way we've been doing so far. Just come in and say y-train. So the same thing for all of the model we're going to look at. So once you define the hyperparameter, you can now move on to training your data. So the point is understanding the algorithm and how they work. That's what makes you data scientists, right? So understanding it and knowing how they work and having an intricate knowledge of it will set you apart, trust me. All right, so it's not just coming to say model.feed, this or that, and all of that. So this is a very essential class, and this is important, and this is very important as well. So let's just move on to the next thing. So as you can see here, we have the summary of all of these kernels here. So using kernels to allows SVM to handle complex non-linear relationships. So the kernel parameter in Scikit-learn specify the type of kernel to use. So as I've just showed you yet, linear kernel is this, polynomial kernel is this, RBF kernel is this, right? Sigma kernel is this. So this is just how to specify your kernel hyperparameter. So in this case, your kernel is going to be a hyperparameter. In KNN, what is your hyperparameter again in KNN? Let's just go back. In KNN, what was your hyperparameter or our hyperparameter? Exactly. So K is our hyperparameter for KNN. For SVM, our hyperparameter, like we have several, but the key one is our kernel, right? So that's how we that's basically how we that's how we like work with SVM. So let's just move forward. So we have disadvantages and advantages, the same way we have for KNN. So SVM is effective in high dimensional spaces. So if you have the data set that is of high dimension, you can actually use SVM. It's going to work very well, right? It's actually going to be efficient in high dimensional data set. So it's also versatile as well because of the kernel function I explained. It's also robust against overfitting. So I'll explain what overfitting is in one of our next classes, okay? So it is robust against overfitting, especially in high dimensional space. So overfitting is something that you want to avoid when you're building a model, right? And overfitting is usually, you are prone to overfitting when you have a lot of dimensions, a lot of features, right? So for SVM, it actually tries to prevent overfitting. It avoids overfitting in a way. The way that algorithm work helps you avoid overfitting. So those are the advantages of SVM. So let's look at the disadvantage. So for SVM, it is computationally intensive, especially when you're working with large data sets. All right. So when you're working with large data sets, you actually have to use a lot of computing resources. So that is one. So if you have a lot of computing resources at your disposal, that's fine. You don't have to worry. So the performance can be sensitive to the choice of kernel and parameters, obviously, as I've said. So you have to be sure that you're using the right kernel and all of that. So if you are working on non-linearly separable data and you want to use linear kernel, you're going to get a very bad model, all right? So that won't give you a good hyperplane. So it is also less effective on data set with significant noise and overlapping classes. So when you have, remember when we are working with non-linear separable data, your data dimension, the dimension is projected to a higher dimension. But when you have classes that overlaps a lot, all right? When you have classes that overlap a lot, it's going to find it difficult to kind of find an optimal hyperplane, all right? So obviously there'll be errors, but it will not be as clean as when you have classes that don't really overlap so much. So these are some of the things that you need to keep in mind when selecting a particular model. So this is all we have for SVM. You can just go over it, and I believe you'll get to understand it very well. In conclusions, SVM are a robust and versatile classification algorithm suitable for a variety of tasks, especially those involving high dimensional data. So when you have high dimensional data, SVM is very good, and it will perform well. So at this point, I'm really rethinking this going into ensemble learning, right? So I might just look at just one. You might just look at this particular material, and maybe we can just see how we do the ensemble learning on Saturday. Okay, so we can actually go to bed because it's already getting late. Or those of us that want to do other stuff. So that's it for SVM. Now we'll look at the last one in the material, which is decision tree algorithm. All right. So we have what we call decision tree algorithm. So this decision tree algorithm is a very regular algorithm that is not just for machine learning. All right. Someone is asking, can I give you a typical real life example of a high dimensional data set? Can someone just answer? Like, I think I've said it several times, so maybe she missed it, but can someone just answer? Let me see if anybody got what I explained. Like, I told you what a high dimensional data is, so can someone just like be kind enough to answer a question before, if there is none, I will do that. So I just want to see if there was anybody that kind of understood the explanations and everything I've said so far. All right, so let's just move on as we are answering. We have decision tree algorithm. So this decision tree algorithm is a type of supervised learning algorithm. All right. It's also used for classification and regression tasks, and they are quite. It's a very interesting algorithm, actually. Right. Decision tree is something that is used like in different areas, right? Not just machine learning. So it was adapted and brought in as an algorithm, and we're now using it to create machine learning model. So decision tree basically works by splitting your data set into subsets based on the value of input features. It's just like creating a tree, an upside down tree. So imagine a tree right now. A tree has what? Leaves, and then it has branches, and then it has the stump, and it has roots, right? So we all know what a tree is. I don't have to start breaking that down for you, right? So now imagine a tree, and then turn it upside down, flip that tree upside down. You would have a decision tree. So that is the structure of a decision tree, a flipped tree. So in decision tree, we have the roots at the top, and then we have branches, and then we have leaves. So that's how the decision tree algorithm is structured. So I just want to give you a visualization of the structure first before we begin to break it down. So that's what the decision tree is. Now, so how do they work basically? So it works by splitting your data set into subsets based on the value of input features. All right. So now let's just use an example. This is a decision node. So basically there are some terminologies you have to get used to. So we have what we call a node. Nodes are the different points of split in our decision tree model. All right. Nodes are different points of split in our decision tree model. I hope everybody is still following, and I hope everybody can still see my screen clearly and hear me clearly. Please, I need responses to know I'm carrying everyone along at this point. Is there any point of confusion or anything basically? So let me just even give you an opportunity to ask any question that you need clarification on at this point. So I'll just give you a few seconds to do that before I proceed. I really, really want you to understand what I'm explaining this night, because obviously you're dedicating 2 hours of your time, so I don't want it to be a waste. Okay. All right. Let's have it. Let's have it. the node, is this similar? Is it like similar to the nervous system? Not necessarily. I think you should just use the explanation of a tree to understand it. So the nodes in this case are like branches, basically. So you can imagine a tree having a root, and then the root now branches and then now moves up to produce branches. So a single branch, a branch can have another branch. All right, it's very possible, and that other branch can have another branch till you have like maybe a termination where you have leaves. So the leaf is like the end point of a tree. Like after a leaf, you don't have any other thing, basically. All right. So that's how a decision tree is. So as I said, flip a tree upside down, and then that's how the structure of a decision tree is. You have what we call nodes at the starting point. So nodes is like the different points of splits, basically, in a decision tree. So now you might be asking, what do I mean by split? What are we exactly splitting? So in decision tree, what we are splitting are the features. All right. So we are trying to split the features in a decision tree. So just think of decision tree as a flow chart. You can also think of it as a flow chart where you ask series of yes or no questions to reach a particular decision. You can say, let's say you want to make prediction for a cat prediction. Let's say you are trying to create a model that can predict if this particular object is a cat or not. So you can ask the first question: does this object have two eyes? Right. So if you have a particular feature in your data set that corresponds to the number of eyes, so you can say, okay, does this particular object have two eyes? You have either yes or no. So if it is yes, you are going to split it, and then if it's no, you're going to take it to another branch. All right. Then you now split based on that yes. So for that yes, so you say for those cats that have two eyes, does it have maybe a tail or something? So you're now adding, as you're splitting, you're adding the feature that you splitted before to the new feature. So let's say for the new feature, you have three categories, right? Or let's say two categories. So having a tail can either be yes or no. So for your yes, you're not going to have, okay, this particular object has two eyes and it has a tail. And then at the termination, they're going to have either of the class. So let's say you are predicting whether an object is a cat or not. So it's a binary classification. So the classes can be either yes or no, a cat or not a cat. So yes or no. So at the end or the what we call leaf node, you are going to have the class itself. So this leaf node will contain that class, right? So let's say the class you're trying to predict is a binary class of yes and no. So this place you're going to have yes or no. This place you're going to have yes or no. So the yes or no will be determined by the split we've been making so far. All right. So in this case, we might have, let me see, I think there should be a diagram here. Just give me a minute. Let me see if I can spin out an illustrative diagram to explain what I'm saying. Because I think the best way to explain is by illustration. And machine learning is data science generally had a lot of theoretical concepts that can be represented in diagram, but the ones that can be represented, we'll try to show you. So that was why the other day I sent us a website link, or I demonstrated using a particular website where we can like visualize how linear regression works by moving the intercept and slope, right, to get the minimal error. So once you see this kind of things, it kind of stamps in your head and you don't easily forget it. So let's see. Let's see. So this decision tree generally is like it's not necessarily an original machine learning concept. It's something that you can use for your everyday decision making. Okay, the ones I'm seeing are just similar to what I have already. Right. So the decision tree algorithm is what you can use for your everyday decision making. So let's assume you want to go outside, or you want to go out with a friend. So you want to determine if you want to make a decision, like either a yes or no decision, whether you'll be going out with that friend or not. And that your decision will be based on certain conditions. All right. So we can also consider these different nodes conditions, basically. So if the conditions are met, then you are going to select the particular answer, whether yes or no. So let's say for the conditions you're going to be looking at while for going out, you'd have the condition of the weather. Let's say if the weather is good, then you'd go out. That is the first condition, but it will not be based on just that condition. It would have to be a combination of different conditions. So it will be, if the weather is the weather good, yes or no. So in this place, the first node will be, is the weather good? So it can either be yes, this particular node there will be yes, and this one will be no. So for this yes here, obviously for this no, the decision is going to be up to no, I'm not going to go out, because if the weather is not good, you can't actually go out. There's really nothing else. So you've actually terminated this particular node here. So there's no further splitting again. So, but for this yes, you can actually make further splits. You can say, okay, if the weather is good, fine. So if the weather is good and I have an outfit, so the next node here will be, do I have an outfit? So the two options here will be yes or no. So if the weather is good and you have an outfit to wear, then you are going to land in this particular decision. Let's just add this under decision node. So now there are two conditions to go. If the weather is good and you have an outfit, so you can even make further split. So if I have an outfit and I have enough money, so now you have three conditions. So if the weather is good, and you have an outfit and you have enough money, then you go out with your friends. So this is a kind of this is a very simple illustration to show you how decision tree works. So these different conditions that you use to determine whether you go out or not, they correspond to the features we have in our data set. All right. So depending on the feature we are going to have different splits here. So what we are going to be splitting actually in a machine learning task are the features, and the split is what is the key thing that happens in decision making. All right. So before you make a split, your machine learning algorithm would have to select the best features to split, and the selection will be based on what we call entropy. Now we are entering another dimension. So entropy basically is a concept that tells you the randomness of a particular thing. All right. So entropy is what is being considered when making a split. So you take a particular feature. All right. Let's say whatever feature it is you have in your data set, you take each feature, actually all the features, and you calculate the entropy of each feature, and then the feature with the least entropy. All right, you want to have a pure split basically. So the feature with the least entropy will be selected as the first feature that you split. So once you select that first feature, then you now split that feature. If it's a categorical feature, it will be very easy. You just split it into the different categories it has. If it is two categories, you split it into two categories. If there are three categories, you split them into three categories. If there are four and the likes, you split them into the number of categories it has. But if it's a numerical feature, then the split will be based on a particular range. All right. So let's say the numerical feature, the range of the number in that feature is from, let's say, 5 to 20. So the split will be based on, let's say you say greater than 5 and less than 15, greater than 15 and less than 20. So your algorithm is actually going to select the different split for you. You don't have to do all of that. I'm just telling you exactly how it works. So, but a split will have to be done. The first thing that will happen here, I think there are steps here. Let me just move with the steps basically. So how does a decision tree work? So the training phase basically happens at the start of the root node. So the best feature is selected. Remember I explained this. So before you make any split, you have to select your best feature. And the way you select the best feature is by calculating what we call entropy. We can use entropy, or we can use what we call Gini impurity. So Gini impurity measures the impurity of your feature, right? So you want to select the feature that is the purest, or that has the least impurity or entropy, right? So entropy is a different metric. Gini impurity also is a different metric. So you can select either of them to use for splitting, all right, to use in selecting your feature. So once you've selected that particular metric and you've calculated the Gini impurity for all your features, the feature with the least impurity will not be selected as the first feature to split. So the split will not happen. So once you've done this first step, then you now split the data based on the best feature. So you put the best feature at the decision node, that is the root node, and then make your split. So that same process will be repeated recursively for each node. So you continue that same process you did. You now choose and you exclude that feature that you've split, and then you now bring all other features and then calculate the impurity and select it and then split it until you got to a point where you can't actually split again. All right. Although there are different stopping criteria or stopping conditions, which we are going to look at. So you repeat this process recursively for each child node. So child node are the nodes that follows the root node until one of the stopping conditions is met. Okay, so there are actually stopping conditions. So there are different things that will determine when your splitting stops. So it is a recursion process. If you are familiar with recursion is a repeated process, something that repeats, like it calls itself, like it is a function that kind of calls itself. A base, you have to define a stopping condition. So your stopping condition can either be maximum depth or minimum samples per leaves, or you just leave it to when it can split again. All right. So that is basically how the training works. So once you've achieved that particular split, the particular split for each feature, they're going to have a representation, right? A decision tree representation. So that representation is your model. So if you want to make a particular prediction and you have some features that you have, so you want to, based on those features, you want to make a prediction, then you now start walking through all the nodes. So let's say you have 4 features, and for your 4 features, you have different values. So for each value, you're going to check the node if it meets this criteria. So you move in this direction. If it meets, you meet it. So until you get to that leaf node where you have the class that you want to predict. So depending on the feature values you have, you're going to have a particular class value. So that's basically how decision tree works. All right. So don't think so much about it, right? It's a very simple stuff. It's very straightforward, but it can become complex with increasing number of features, right? So normally in Scikit-learn, I think there are libraries that can actually help you visualize your decision tree split. So once you create a decision tree model, there are actually libraries that can help you visualize the tree itself, right? So I think I won't have time for that actually, but there are libraries. I might give you a reference material to look it up. But once you create a model, you can actually see that, you can actually know how your model is making predictions. So decision tree is actually one of the most transparent model, right? That you can actually know what is happening and how it is making its decision. All right. So that is how decision tree basically work. So for prediction, once you've trained, right, and you want to make prediction, I just explained that. So you actually traverse the tree from the root node to a leaf node, making decisions based on feature values of the input sample. All right. So that's basically how prediction works. So you get the label that is on that particular leaf node and assign it to the data point you're trying to predict. So this is actually a lot, and like I can understand how complex it is sounding, but I've said it over and over again. There is nothing that you can't understand. Like the only thing is just trying to the only thing that's stopping you is just you taking your time to go over it at the pace in which you can assimilate. All right, the pace at which I'm going might be too fast. It might not necessarily be too fast, but you might need to actually take a particular section, take a step back, break it down, try to understand it before moving on to the next thing. But what we are doing is that we are trying to explain everything, moving from one point to another point, from one point to another point. So everything is just scattered in your head, and you're trying to organize and all of that, which is very fine. So what you do is that the recording will be made available. So you can just take your time, go through it, and try to get the point at each step and all of that. So you definitely get clarity on it. So I was once at this point where these things were not really sounding very well, and now I've kind of understood them well enough to explain it. So that's just it for decision tree. The implementation is the same, and actually this is even why most times people with background in mathematics, people in background in computer science actually find these things easier, or these tech skills easier to get than people that are not coming from this kind of background. So you that are not coming from a background that taught you some of these underlying concepts, you need to put the extra work, extra effort to understand them. And there are a lot of things that we talked about now that you might not have heard of before, but some people, because of their background, they already know what entropy is, they know what recursion is, they know what some of these things are. So it's easier for them to put one and one together and get the idea formed in their head. But you don't know what this underlying concept means. So you have to actually take a step back and try to understand those concepts first, given your background, all right? So it doesn't mean you can't learn. It means you just need to put the extra effort. All right. So you need to put extra effort into understanding some of those things so that you can actually put them together and make sense of it. Okay. So that's basically what it is about. That is what it is to this. It's really nothing complex like that. It's just for you to understand some things. So that's it for decision tree. So there's some key concepts we have. We have root node, we have decision nodes, we have leaf nodes, we have splitting, we have pruning, we have impurity measures. So these are the things I've explained already. So you can basically just look at them on your own. So impurity measure is one of the very key thing in decision tree. So it's it's one of the key stuff in decision tree that determines how your split is done. So you have gain impurity, you have entropy, and you have information gain. All right. So you can select either of these three. Someone is asking, don't ask the question, so let me just okay. I think that's what's meant by until one of the topic. So you can actually set the condition yourself. So we're going to show you in the implementation. These are you implement decision tree. So you import it from this particular module, sklearn.tree. Let's go on and show us how we do that. So we say from sklearn.tree import decision. So we have classifier and regression classes. So you can just say decision tree classifier. All right. So you can also import the regression one as well. So import decision tree regression. So if you run this, you're going to see that we have some hyperparameters here that we've looked at already. So we have criterion. Now this criterion is what I explained. So this criterion is the Gini impurity, the entropy, the information gain, right? So this is the max depth as well. So max depth, if you set max depth, then your tree will stop when it gets to that max depth. The max depth is actually the number of nodes that you have, all right? So the number of nodes. So if you don't set the max depth, it will continue splitting till it can no longer split again. But if you set max depth, it will split till it gets to that number of depth, or the depth that you've set it. So let's look at the different hyperparameters. You see the criterion here. We have Gini, we have entropy, and we have log loss. So this is information gain that we looked at here. So this criterion, the function to measure the quality of a split, which I've explained. So the supported criteria are Gini, log loss, and entropy, and all of that. So for both, okay, information gain is log loss and entropy. So this is exactly what I've just explained. So it's just the implementation basically. So this is the max depth where I also explained. So the maximum depth of the tree. So this is the maximum depth of the tree. If you don't select anything, then all nodes are expanded until all leaves are pure, until all leaves contain less than minimum sample. So there are a lot of things to actually look at when it comes to parameters. So it's a different class on its own. So I need you to understand the idea behind this algorithm first before we move on to that. Okay, so that's basically it for decision tree. So you just import it and follow the normal step. You can come here and say tree, and you just come here and say decision tree classifier, and then you can select max depth actually. So you can say max depth 50 or whatever. So your max depth is something that you can actually fine tune as well. So if you have a lower max depth, you can it would not give you, it might not give you a good performance. So you might need to increase your max depth and all of that. So if you leave your max depth to continue to be none, your decision tree will split till there's nothing else to split. So you can actually cause overfitting. All right, overfitting is something I explained. If you decision tree is very, very prone to overfitting, right? So that's something you need to know. So this is how you implement. Implementation is not a problem here. It's just to understand what is happening, right? So you can select either of these different classifiers and use them for your project, or you can try several of them and compare their metrics and their performance. So let's conclude with that. So these are the advantages and disadvantages of decision tree. So decision tree is simple to understand and interpret, as I've said. You can actually interpret it. It requires little data preprocessing. Yeah, it actually does. It requires little data preprocessing. We're going to talk about that later on. So you can handle both numerical and categorical data. It performs well on large data sets, and it's capable of modeling complex relationships. It captures very complex relationships. These are the disadvantages. It's prone to overfitting. So this is why I said it's actually prone to overfitting. It can be unstable because small variations in data might result in completely different tree. It does not support online learning, and it is biased towards features with more levels. So these are some of the disadvantages of decision tree. So you can read them up, and these materials and videos are available for you to actually look at and try to assimilate. And yeah, so that's it for decision tree. So in conclusion, decision trees are versatile and easy to understand, and it's a very popular choice as well. And you can just practice with it and just include it in your project as well and see how well it's performing. So these three trees I just explained to us now, they are actually very good, right? They perform well, but compared to these ones that we have here, they are still learning. Okay, so they are what we call ensemble learning. We're not going to look at this. I just want to introduce it to you. They're what we call ensemble learning. So ensemble learning basically is an approach to machine learning when you combine different algorithms or different models together. It's just like bringing three heads together to make a prediction. Let's say, for instance, you have a class and then you ask a question in that class. So normally you would expect each person to answer that question, right? So if probably you have 20 students, you expect each of them to answer the questions individually. That is your normal machine learning. So imagine each of those students as the machine learning model. So they have the ability to make predictions, which is answering questions. So they can actually do well or not, depending on their knowledge. So when we come to ensemble learning is when you now bring different models together to answer one question. So it will just be like now grouping your students in that class into like 5, 5, 5, 5, 5, 5, 5. And when you ask the question, you don't expect each of them to answer it individually. You expect a group to answer that question. So 5 of them will now have to put their heads together to answer the question. So the chances of a group getting the answer is higher than individuals getting the answers. All right. So that is basically what ensemble learning means. It kind of ensemble or brings different models together to produce or make a prediction, basically. So we have different ensemble learning techniques, right? We have some of the models here, which we are going to look at later on. So we have ADA boost, we have gradient boost, we have SG boost. So these are some of the algorithms we're going to be looking at. So remember when I told us about SG boost at the beginning? Now this is where it falls under. So we're going to look at them, and it's actually it's very interesting subject or concept to look at. And trust when you understand it, you'll probably be using them most of the time because they perform very well. Obviously, they perform very, 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 very well. So I'm not going to be looking at this ensemble learning today because of time. So we're just going to be like wrapping up here. So hopefully we get enough time later on. Just we are going to be looking at for today. I really hope the ones that I've explained so far, please, to an extent, you got to understand it, right? You got to understand it. So at this point, I'm going to be like taking in questions. All right. So if you have any question that you want to ask, please just indicate. All right, so please, I am going to be taking like maximum of 5 questions. All right, so Justice, you have your hands up. So, Manfred, please ask a question.
Yes, my question is on the criterion that the algorithm used to select when splitting the tree, like which to use, whether entropy or the Gini impurity. I didn't really get that clearly because I know what entropy is and you explained what Gini impurity is. So what is the criterion for the algorithm to select each of them when splitting the tree?
Okay. So the thing is that the criterion itself, it's a whole another entire algorithm on its own. Okay, so basically the split, what makes a decision tree, what makes it a good model is how well you split your data. So the split is going to be done by either of the criteria I mentioned impurity, and we also have entropy. So what is criterion, or what is algorithms try to measure is how pure the feature is. So they do that by actually splitting the data set basically and measure how much they measure misclassification rates basically. So when you look at classification data set or features that have categories, what the criterion is that to split the features into those categories, right? And then measure how impure that a particular split is. So there are different methods it uses in calculating that. Like, I really don't want to go in there. That's why I just breezed over it and just set criteria. So it's probably when you are in an advanced class or there's enough time that we can actually, so because I love there's some mathematical stuff that goes into it, and the explanation is going to actually could probably confuse you a lot or convince a whole lot of other persons that are just trying to understand the basics, all right? But I need you to just understand that the split itself is based on either of these criteria. So Gini impurity is a method of splitting, while entropy is another method of splitting. So what these criteria measure? They measure the impurity of your feature. So that impurity itself is what I believe you are trying to understand, which explaining it is going to be a whole lot of, we can actually dedicate an entire class to understanding how they determine, how that particular criterion determine the impurity of a feature. All right. So just have this at the back of your mind. Just understand this fundamental, these basics first. Then we can now see how if there's chance, which I really don't think so, probably look at that, or I can just send in materials or videos that might explain it better to you. Okay, so just try to understand this higher level concept first. Like, I'm actually always intentional about not going too deep at the first explanation, right? Because I understand how we can complicate things. So understand this one first. If it's something you want to understand better, then you probably can ask him maybe after the class, and if I have enough time, I will then just take my time to explain it. All right.
Thank you, sir.
So I hope that's good. So Justice, your hand is up. Please ask your question.
Sir. I really want to appreciate you for taking this time to teach us and also sharing your knowledge with us. Okay, my questions is prior to our previous classes concerning standardization and also imbalance. You make a mention about standardization is actually good for outliers. Data have outliers. So if we are using some models that are not good, like we are standardizing our data, like our features. So if we are using models that are not good on maybe on data that have been standardized, will it actually affect those models, or is it okay to just do that so that it will
Sorry, please, can you just like track back a little bit? I didn't get you. Like just like few
okay.
track back a little bit.
Concerning the standardization, that there are some models that are okay with their features being standardized. Then if you're using other models that their features are not okay with, like with data sets being standardized, will it be okay for us doing that? And also, my second question is on imbalance target variables. If we are using some models are also good on imbalance variable, but you said something that if we have a data set that are target variables, that their model is I should look for a way either to balance it or do some. So is it okay to use them that are okay or impact? Those are questions.
Okay. I think for this question, I spoke about to for what our distribution to standards. So obviously we get before you get of pre-processing, you should have dealt with your outlier already. You should have like just figure out what your outlier is and see how to do that outlier. You most likely not even have an outlier in your data. So you be good. So, but if let's say in a situation where the outliers can't be entirely eliminated, then I mean to say like sensitive, right? So you have outliers that you need to work on. The outlier is can't be entirely there personalization because them. But if you eliminate it, then you normalization. And I don't want to think so much about this. First of all, just do your go through the process normally. When you now start seeing the ideal way to do it or the pragmatic way to do it is going through the process first. All right, because if you try to check everything at every step, you will definitely not finish on time, or like you'll just be stuck somewhere because you want to get everything perfect. Just go through every step. Just pick a particular technique, right, that you feel will be good. Go through it and then get your model done and check the performance. So what will basically make you track back to checking all these things is when your model is not really performing well, then you now start checking all the different parts of your building process to see if there's anything you can change or if there's anything that could have been done better that would improve your model, right? So you kind of do it bottom up instead of top down, all right? So you do everything once and then you now start tracking back. It is easier that way to figure out what the problem is, okay? So it's when you finish something that you can now start checking to see where the problem is coming from, right? Because when you tweak something, you check again to see if it has improved it or not. If it has improved it, then you know that, okay, this is what was done wrong or this is what I should have done. So that is the pragmatic way of building a machine learning model. And yeah, it's actually going to save you a lot of stress and a lot of time. So I kind of understand where you're coming from, but just take this approach and I think it will be easier for you. So there was a second question you asked, and I think I've lost track of the question. Can you just like remind me of what this question is?
Okay, I was talking about the target variable being imbalance. You said
Okay.
if the target that some models are like with it, why some are not. So is it okay for us to make that target variable to be balanced, or we should go with models that are actually good with imbalanced target variable?
Did I ever mention some models being good with balanced or imbalanced? I think what I remember mentioning was metrics, like is a metric. Okay, you want to say something?
No, like why making research on like most of the models that you have taught us? Like I saw that some of them are actually good with imbalance data set, like imbalanced and target variables. So I was like, okay, is it okay to go on with it, or I should just balance the target variables and move on? So that's why like I'm getting confused if I should balance it or I should
So
just use models that are okay with that kind of.
So the thing is that using models with model that are quote unquote good with balanced imbalanced data set, it doesn't really give you the entire picture because of it doesn't give you the entire picture of how well your model is performing because you still have to check the metrics, but your metrics is what will determine whether that model is still performing well or not, right? So when you create your model, with whatever model you are creating, you still have to like go through the metrics. So your metrics is what inform you or let you know how well that model is performing, right? So whether they tell you this model is good with balanced data set or not, at the end, you still end up with the metrics. So the metrics will point to whether you are doing something right or you're doing something wrong. So I think the approach I I said in class is just the best. When you have an imbalanced data set, although there are techniques to balance your data set, but that's actually out of what we are doing. It's actually an advanced stuff. But for now, you just use your metrics to guide yourself. Like, okay, obviously, in this case, I can actually use accuracy to determine how well this model is performing, because it will be biased based on the distribution of the classes. So you can now like start using the different metrics that you have, checking mostly you'll use ROC AUC score to actually compare across models. You can use your check your precision as well, check your recall, check your F1 score, and other metrics that I've mentioned. So I think this would give you a holistic idea of how well your model is performing, right? So regardless of what model you are using, you still have to fall back on the metrics itself. That is just what I'm going to say about it. So the metric is what you should pay attention to, all right? So if the metric is not giving you what you want, then you can now start checking all these things like, okay, let me try to use this model that I saw online that they said is good for imbalanced data set. If you use it and your metric improve, then fine. But at the end of everything, your metric is what you still fall back to. Okay, let's assume you use it and it's not good. Then you can now start checking or considering stuff like balancing your data sets and all of those things. So these are guidelines that you should follow, right? You should try to follow this guideline first and build up from there. So you don't just get a lot of stuff to check when building a machine learning model. It's not as straightforward as it sounds, especially when you're building something that people would use, right? So you need to check a whole lot of things. You need to actually like take your time, iterate, and ensure that yes, this stuff is actually performing very well. So you do the simple things first before you now start like adding extra stuff to it. So you don't try to add a lot of moving parts. You make something simple and you build from it, right? So that way you can actually it will be easier for you. But if you try to build, let's just take for instance the people that the Wright brothers that made planes. If they try to build this kind of planes that we have today that are sophisticated and they have a lot of moving parts, they would end up not making anything, right? But they actually did something very simple, something that can fly, that had the necessary parts to fly, to take off. So they did that, and from there they now started adding parts. So that's the approach I needed to take when building machine learning model. Do the simple things first. Just follow the simple process, and when you get to the end, then you can now track back and start iterating from there. Start trying to see if you can add some things to make it better and all of that. So I feel it's just going to be easier on you and be less stressful for you generally. So I think I hope that actually answered your question and helped you. So I'm tired at this point, honestly. I actually did this out of sacrifice because I have work I'm doing during the day. So I need to go off at this point, and you all also need to go off as well, so we can rest and enjoy the holiday tomorrow and come back on Saturday for another class. All right. Thank you very much for your time. Joseph, I can see your hand, but to be honest with you, I can't take another question. Just drop it in the group chat, and I'll try as much as I can to answer the question. So thank you very much for your time. The recording will be made available for those that are not present here, and for those that are present, it will also be made available for you, so you can go through it over and over again as many times as you want to. So we're going to be closing the curtain at this point, and I'm also going to ask you to drop what you learned in today's class. There's no way you didn't learn something. Like there's no way you didn't learn something, no matter how complex this class sounded. There's no way you didn't pick up something. So that thing that you learned, please say it. Let me know. I want to hear it. I want to see it. Yes, thank you very much. Do have a beautiful night rest, and yeah, see you on Saturday. Good night.